Hello students, over here we are going to study the application and the instrumentation process of flame photometry in a little more depth. The first thing we'll study is the principle of the photometer. Now what is the principle of a flame photometer? The compound of the alkali and alkaline earth metals, that is group 2, dissociate into atoms when introduced into the flame. Okay, so over here let us first see what are alkali metals. Alkali metals are the metals which come under group 1. Those are lithium, sodium, potassium, rubidium, cesium and francium. Alkaline earth metals are the metals which come under group 2, which are bromine, magnesium, calcium, strontium, barium and radium. Group 1 and group 2 come on the leftmost side of the periodic table and they consist of S block. Almost all the metals, that means generally all the metals over here are metallic in nature. All these elements are metallic in nature and they dissociate into their respective particular atoms when they are introduced to the flame. Based on this principle, the entire flame photometer works. This principle is very important. Some of these atoms further get excited to even higher levels. So now what does the flame do? The flame gives excitation to that particular atoms. The excitation level of those atoms increase. Because the excitation increases, those atoms get energy. Now this energy leads to a discharge plasma state. Now there are certain atoms which further get excited to a higher level. But these atoms are not stable at higher levels. Always remember, energy and stability are inversely proportional to each other. Higher the energy, lower the stability. Higher the stability, lower the energy. We can relate to a daily life as well. If we have a lot of energy, we will not just sit stable at one position. We will walk around, jump around, dance around. That means our stability is less. But if we have less energy, for example, we have worked the entire day and at the end of the day now we are tired and we have less energy, that means at that point of time the energy is decreased. If the energy is decreased, the stability increases. When do we sleep at night? When we are extremely tired, we go to sleep at night. That means our energy levels are low and the stability becomes high. That means we are stable. We are at one position, we are sleeping, we are not moving around. Why does this happen to us? Because even we are chemically made up. We are made up of substances. In the same way, for these elements and these atoms also, that is true. So higher the stability, lower the energy. Higher the energy, lower the stability. Hence, these atoms emit radiations when returning back to the ground state. So if we have a particular atom which is at a very high state, and that particular atom has to get back to the stable state, then from that high energy level to the stable level, what will that atom have to do? It will have to emit energy. Let's relate this to a daily life example. What if I have a lot of energy right now? Will I be able to sleep? No. Why? Because I have a lot of energy in me. So what will I have to do? I will have to do a lot of work. I will have to do a lot of activity. I'll have to be active throughout the day. So when I am being active throughout the day, I'm actually radiating my energy. That means I'm actually giving away my energy to that particular work or that particular activity. Once that is done, I will be able to get into a stable state, the ground state or the sleeping state. That is the reason why we have cycles of day and night. Why do we have that? Because when we sleep at night, we are energized, so we can use up the energy in the day and then again take rest at night. In the same way for atoms also, atoms emit radiation. These radiations, while returning back to the ground state, that means when these particular radiations return back to the ground state, they will have to emit the energy away. Once the energy is emitted away, they can come back to the particular ground state or the stable state. These radiations generally lie in the visible region of the spectrum. Now, whenever we talk about spectrum is nothing but variations of different levels of light. Some of these radiations are visible to the naked eye, some of these are not visible. Even if they are not visible, they are there. We know that they are present, but they are just not visible. So now what happens is, whenever a higher energy state atom is coming back to the ground state, when it comes back to the ground state, it emits the particular light. Now when it emits that particular light, that light is visible to our naked eyes, and that is the reason why it falls under the visible region of the spectrum. Each of the alkali and alkaline earth metals has a specific wavelength. Now this is very important. What is wavelength? Each and every element will have different wavelengths. Some wavelengths will be high wavelengths, some wavelengths will be low wavelengths. But these wavelengths are different. That means the wavelength of lithium will be different from the wavelength of potassium. The wavelength of potassium will be different from the wavelength of barium or the wavelength of cesium for that matter. That means alkali and alkaline earth metals have specific wavelengths, and these wavelengths are very unique to that particular element or that particular metal. We cannot merge two wavelengths together, or two elements cannot have the same wavelengths. Based on these wavelengths, we come to know which particular metal is present. So over here, if you see, we have sodium, potassium, barium, calcium and lithium. 5 elements. Sodium belongs to group 1. It is an alkali metal. The wavelength is 589 nanometers. Now nanometer is a measuring unit. It's a measuring unit of distance. The way we have centimeters, millimeters, kilometers, in the same way we have nanometers. It is much smaller unit of length. And when sodium emits energy, the wavelength is 589 nanometers, resulting the flame to be of a yellow color. That means that particular sodium gives out yellow color. Moving on, we have potassium. Again, it belongs to group 1. Group 1 is alkali metals. The wavelength is 766 nanometers. 766 nanometers gives a violet color, and thus the flame will be resulted in the color of violet. Barium is the third element given over here. Barium belongs to alkaline earth metals. It belongs to group 2 of the periodic table. And if you see, it has a wavelength of 554 nanometers. The wavelength of 554 nanometers gives a lime green color. Thus, the flame itself would be of lime green color. Next element given over here, the fourth element is calcium. Calcium has a wavelength of 622 nanometers. 622 nanometers is the wavelength of calcium. That means that is the unit. The one wavelength of calcium is 622. It is orange in color. The color of the flame will be orange when calcium is present. Calcium itself belongs to group 2 of the periodic table, the alkaline earth metals. Finally, the last element we have over here is lithium. Lithium belongs to the group 1 of the periodic table. It is an alkali metal, and the wavelength of lithium is 670 nanometers. That means one wave, the length of one wave of lithium will be 670 meters. And it gives us a reddish brown flame. That means it gives us a darker shade of red when it comes to lithium. So these are different elements, or I might say different metals, belonging to the first two groups, group 1 and group 2, that is alkali metal and alkaline earth metal of the periodic table. and they have certain amount of wavelengths giving us certain colors. For certain concentration ranges, the intensity of the emission is directly proportional to the number of atoms returning to the ground state. Now, this particular statement is very simple. It talks about the intensity of emission. How much is the emission happening? Is the emission concentrated or the emission diluted? And how do we come to know that? It directly depends on the number of atoms returning to the ground state. If I have many atoms returning to the ground state, that means the intensity will be really high. If I have some or little atoms returning to the ground state, the intensity will be comparatively low. So that is the reason why the concentration ranges, or it depends on the number of atoms returning to the ground state. And the light emitted is in turn proportional to the concentration of the sample. So for example, if I have a particular element and that particular element is going to give away yellow color. So if it is going to give away yellow color, then that element should be in good amounts, in good proportions. There should be many atoms of that element which are supposed to return to the ground state. If that is possible, or if that happens, then the color will be really good. If not, then the color will be faded. Moving on, we have parts of flame photometer. A simple flame photometer consists of the following basic components. Let us see these components, the basic components of a flame photometer in detail. Source of flame. We should always know the source of flame. A burner in the flame photometer is the source of flame. Generally, during any kind of chemical reactions or any chemical transactions in the laboratory, whenever we are using a flame, we generally use a Bunsen burner. Burners are generally 90% of the times sources of flame. It can be maintained at a constant temperature. So the source of flame should be at a constant temperature. Now we cannot have a flame with a very high temperature or a very low temperature. And the temperature being variable and keep on shifting. We have to make sure that the flame is set up at a particular point and it remains at that point even after a long time. The temperature of the flame is one of the critical factors in the flame photometry. The entire flame photometry happens because of the temperature. So that is the reason why temperature itself becomes a critical factor, and it is important for us to understand that the temperature should remain constant. Over here, we have different temperatures. So we have two columns. The first is fuel oxidant mixture. Now whenever we do the combustion process, it is important for us to know that the combustion process happens only when oxidation happens. And oxidation happens only when there is an oxidant. So over here we have fuels plus oxidants, and on the other side we have temperatures. The first we have is natural gas. Now this natural gas is using normal air, that is mixture of different gases, that is air, as the oxidant. And when both of these combine, we have to provide a certain temperature, and the temperature maintained is 1700 degrees Celsius. Second is propane. Propane is nothing but 3 carbons in a straight chain. C3H8 is propane. The oxidant for propane is air. Again, we take the normal mixture of different gases, air, and we know that air also contains oxygen in it. So we take air in presence of propane, and the temperature maintained is 1800 degrees Celsius. The third is hydrogen air. Hydrogen is nothing but my H2. H2 is also inflammable in nature, and when we have H2 in air and then we try to combust it, the combustion process starts and the temperature is 2000 degrees Celsius. Now in the next one, what I am doing is I'm keeping hydrogen as it is. I'm not changing the concentration of hydrogen, or I'm not changing anything when it comes to my fuel. But instead of keeping air, I'm changing the oxidant to oxygen. So now the next mixture becomes hydrogen, oxygen. The oxidant from air has now become only oxygen. And hydrogen oxygen mixture is 2650. 2650. Next we have is acetylene and air. Acetylene is again an organic compound. When this acetylene is burned in presence of air or taken to be oxidant as air, it gives us 2300 degrees Celsius. Now this particular acetylene, instead of air, now when it is changed the oxidant to pure oxygen, it gives us 3200 degrees Celsius. So if you see both in hydrogen as well as in acetylene, whenever we are changing the oxidants from air to oxygen, the temperature rises significantly. And because the temperature rises significantly, it gives us a proper increase in the temperature, a proper amount of fuel. Next we have is acetylene with nitrous oxide. So again we have kept acetylene, the fuel, as it is, but instead of air or oxygen, over here we have used nitrous oxide, and this particular nitrous oxide burns at 2700 degrees Celsius. 2700 is the temperature that it gives us. Finally, we have cyanogen and oxygen. Cyanogen and oxygen together gives us 4800 degrees Celsius, which is a good amount of temperature, a good amount of heat produced. The next part we have is a nebulizer. The first was the source of flame. Now the next we have is a nebulizer. Nebulizer is used to send homogeneous solutions into the flame at a balanced rate. Now if we want to maintain the flame at proper degree Celsius, at proper temperature, at a particular constant temperature, it is important for us to also understand that we have to send homogeneous solutions inside the flame at balanced rates. When we are sending these homogeneous solutions inside the flame at balanced rates, what happens is the flame remains at a constant temperature, and this particular process or mechanism happens with the help of nebulizer. The third is optical system. The optical system consists of a convex mirror and a convex lens. Now there are two types of mirrors and lenses. One is concave and the second is convex. Concave is when it is shaped inside in a curve which is going inside. Convex is when it is shaped outside. The curve is going outside. So there are two types, concave and convex. Over here we are using the convex mirror and the convex lens. The convex mirror transmits the light emitted from the atoms. Convex mirror also helps to focus the emission to the lens. The first thing the convex mirror does is to transmit the light emitted from the atoms. Because the shape is outwards, it can easily transmit the light, it can easily reflect the light, and that is very important. Second, the convex mirror also helps us to focus the emissions to the lens. The lens helps to focus the light on a point or on a slit. So this entire thing, focusing the emissions on a particular light or on a point on a slit, is entirely done by the optical system. So the first part was the source of the flame, the second was the nebulizer, and the third is the optical system. Now let us move on to simple color filters. The reflections from the mirror pass through the slit and reach the filter. So after the flame is, we have got the flame, after the nebulizer is keeping it as a constant temperature, and the entire optical system helps it pass through a slit, it reaches a point which is known as filters. Filters will isolate the wavelength to be measured from the irrelevant emissions. So there are various kinds of emissions already happening, but we have to make sure that our emissions, the ones that we want to capture, are the relevant ones and not the irrelevant ones. And this can be done with the help of filters. The next part is known as a photodetector. The intensity of the radiation emitted by flame is measured by a photodetector. After passing through the filters, now we have got the emissions that we actually wanted. And these particular emissions are now sent to the photodetector. And these photodetector will help us to measure the flames. Here the emitted radiation is converted into an electrical signal with the help of photodetector. Now there is change in energy. The emitted radiation, the radiations which were emitted first, are now converted into an electrical signal, and this happens with the help of photodetector. These electrical signals are directly proportional to the intensity of the light. Now finally, these electrical signals are directly proportional to the intensity of the light. So this is how we actually measure the intensity of the light. And because we measure the intensity of the light, we come to know the concentration of the atoms in it as well. This is how exactly a flame photometer works. At the bottom on the left you can see a sample. Then there is an atomizer. On the top, compressed air is supplied with compressed fuel supply to give that particular temperature. We had seen a different table of temperatures ranging from 1700 to 4000. And this particular range happens how? Because we are combining air supply with fuel supply. After that, the entire atomizer, sample and the mixing chamber, all the particles go up and help the flame to maintain a constant temperature. Now that temperature can either be 1700 degrees Celsius or it can also be 4000 degrees Celsius, depending on what the sample is and what the oxidant and the fuel combination is. Moving on, the flame moves to the convex optical system, the convex lenses, which help it move through the slit, pointing it towards one slit. This slit leads to the filter. Now this filter will go to the photodetector. The photodetector will convert it into electrical rays, and this will be published or shown on the LCD display. This is how exactly a flame photometer works. So over here we studied about flame photometer. What exactly is a flame photometer? The principle of a flame photometer. We also studied about how this entire process works. So we studied different components, starting from the source of the flame to different temperatures to be maintained, to the nebulizer to maintaining the temperature. Then the entire optical system, the optical system worked on the convex lenses to make a point that the entire flame points towards one slit. Then the filters were used, which were helping us to detect which is the relevant emission and which others are irrelevant emissions. Finally, moving on to the photodetector, which converted the emission into electrical rays, moving on to the LCD display. This is the entire detailed version of flame photometry. Thank you.